Welcome to welcome to this lesson where we'll be looking at the exponential time complexity. So in the previous lessons we look at the logarithm time complexity where we showed example of binary search which operates on a big O log n, which we explain the algorithm how the algorithm works. So here we're going to be looking at exponential time complexity which works on a big O to n. So exponential time complexity describes an algorithm whose growth doubles with each addition to the input size. So it is among the slowest growing complexities and is typically infeasible for large input. So here we're going to be using a simple example. There are so many examples for exponential time complexity, right? But here in this video tutorial, we're just going to be using just one example to show how an exponential time complexity works. Now, this is a popular algorithm which we normally use in the data structure class, which is 2 of Hanoi, right? 2 of Hanoi. So 2 of Hanoi operates on time complexity of order of 2n. So the 2 of Hanoi is a classical mathematical puzzle that involves moving a set of disks from one world to another and following specific rules. So it is a fascinating example of recursion and is often used to teach algorithm thinking. Now let's show how it works. So before we show how it works, there are rules for two boundaries. So the first rule is only one disk can be moved at a time, right? So a disk can only be placed on top of the larger disk or any empty rod, right? So then the last one is you must use rod B, which is your auxiliary node, right? Rod B serves as your auxiliary node on a temporary storage. So that's what we're going to be showing here. And then now the movement, right? 12-hour movement, or let's call it 12-hour moves, right? So the movement and steps work on 2n minus 1, which means that if we have two disks, right, which means that if n is equal to, let's say if we have one disk, so the one disk should be 2, right? 2 raised to the power of 1 is 2, right? So equal to 2 minus 1 will give us what? 1 moves, right? So let's say if we have n equal to 2, so it becomes what? 2 times 2. Remember, it's 2 raised to the power of n, right? So it means 2 square, which is 2 times 2, equal to 4. Minus 1 will give you what? 3 moves. So what we have n equal to 3. So we have 2 raised to the power of 3, which should give you 2 times 2 times 2, which should give you 8. 8 minus 1 equal to 7 moves. So that is how it operates, right? So when you're doing the moves, right, if you're doing for n digs equals to 3, if you're doing for 3 digs, then the moves from the source pole to the target pole must be 7. So let's just showcase a simple example here. So here we'll quickly use let me do for 2 digs, let me explain for 2 digs, then I will explain for 3 digs, and then we'll write the recursive algorithm, right? So now let me use a table to demonstrate this. So I have a tree table here, right? So I have tree table. So let me put a tree table here. So within this place here. Okay. So now this first one is our source pole. Then this is our auxiliary pole. And this is our target pole. Right. So now, so the basic idea here, so the basic idea here is to, let me just remove this. Let me move this. Let me move this down. Okay. So the idea here is to move our dig. So let's say we have, let's say we have n. Why is it doing this? So let's say we have n is equal to 2 digs, right? N is equal to 2 digs. So two discs, we have the one and the two. You can see the one, let's assume the one is smaller than two, so two is larger, right? So two will be at the bottom. Remember the rule states that a disc can only be placed on top of a larger disc or any empty rod. So in the first place here, we have all our discs placed in our source pole, which is one and two, and we want all the disks to be transferred to our target pool. So how do we do that, right? And the rule states here that a disk can only be placed on top of a layer disk, and only one disk can be moved at a time. And you must use rod B, which is auxiliary node, as a temporary storage, right? So it means that these are permanent. These are our goal, where we want to transfer all the disks down to the target pool. So now n equal to 2, it means that the moves must be 2 times 2 minus 1, which give you what? 3 moves. So it moves and the move must be 3, right? The move must be 3. So what do we do? Now, in order to solve this easily well, and technically well, now there are steps I want you guys to understand here, right? So let's say n equal to 2 and 2 is even, right? So 2 is even, which means that let's assume our source pole is equal to A, right? So let me just drop this thing down, or let me just take it here. Let me take it here. So our source pole is equal to A, then our auxiliary pole is equal to B, then our target pole is equal to C. Our target pole is equal to C. So now for this is even because this is even, two is an even number, right? So and this we have two digs here we want to move to our target pole. So technically the way the moves go, although computer does it recursively, right? But if you're asked to solve this, right, handwritten, and you need to master the move, all you just need to do is, since this is even, right? So it means that even goes through A, down to B, then down to C, right? So you follow this pattern for even. That is for even digs. So now for all digs, you follow this pattern A, C, and B. A, C, B for odd digs. So once you can memorize this pattern, right, so you can be able to know how to make the move. Now we have two digs here, right, and these are even. So if I want to make a move here, the first thing I will need to do here is to transfer the smaller one. Now we have two empty places, the auxiliary and the target, right? The target. Our goal is the target. Our goal is to move everything here to the target pole, right? So now, but we need to move the n minus 1. The n minus 1 is, we have two, right? Two digs, right? So n minus 1, we have two digs. So our n minus 1 is equal to our n minus 1 is equal to 2 minus 1, right? Which means is one, just one disk we are moving, right? Just one disk we are moving down to we are trying to move it until we make space for 2 to get to the target pole, and then move every other items from the temporary storages, from either the source or the auxiliary to the target. So now, since we are dealing with an even number, right? The first thing we need to do is to move 1 down to the auxiliary, because the auxiliary is our B, right? Look at this pattern A, B, C for even numbers. So move 1 to auxiliary here, right? That's what we do there, right? So it means that we have one move now. We have done with one move I've done here. So the next move here is, now you can see there's a space for 2, right? And now we're using the A, B, C pattern for even number. Now the 2 is supposed to move to the auxiliary, right? But the two cannot be on top of one, right? The two cannot be on top of one based on the rule of the Torah of Hanoi. So then the next pole we need to move it now is C. So A, B, C is supposed to be B, then C. So move two here, right? Now the next one is we have moved to the next one we're targeting is one. So now is two moves now. The next one we're targeting is one, right? So now we have one empty rod, which is a source pole, right? Then we have the target, right? And we are in the B, which is auxiliary is B. Now, if you check here, the next move is C, not A, right? Not the source pole. So move this down to the target pole. So you can see how we have successfully moved the one and two, and we have successfully completed our three moves, which gives us 2 times 2 minus 1 equals to 3 moves. Now, what if we have n equal to 3 disks, right? What happens? What if we have n equal to 3 disks? Let me add another example. Let me add another table here. So n equal to 3 disks, we have this, we have 1, 2, 3. Okay, so if you can do for n equal to 2, n equal to 3, it's the same pattern you can do for n equal to 4. Just follow the same principle and you get it done, right? Just follow the same principle and you get it done. It's very simple. So I have my table here. So this is for n equal to 3, which becomes 2 times 2 times 2, it becomes 2 times 2, 4 times 2, 8 minus 1, which is 7 moves, right? So that means the move must be 7 to complete our the moves must be 7, like to move 1, 2, and 3 to the target pole, it must be 7, right? So we have this is our A, which is our source pole, this is our B, which is our auxiliary pole, and this is our C, which is our target pole, right? So now let's make our move now. Now you can see that n equal to 3 is odd, right? N equal to 3 is odd, so we have to follow this move, right? A, C, B. So now we have 3 disks. So the first thing we need to move is smaller disk first. Which one? Now we have, so the first thing you can see, follow this pattern, we move 1 to C, right? You move 1 to C. Then the second one is to move this 2 now, right? So following this pattern, 2 is already in A, 2 is supposed to be in C, right? But 2 cannot be on top of 1 because 2 is larger than 1, so 2 comes here. So now we now have 2 iterations, or 2 moves, right? 2 moves now, right? 2 moves. So the next thing here is we're supposed to move this larger number, but we can't move it because the larger number cannot stay on top of 2, it cannot stay on top of 3. So the next thing we do is to move 1. Right, 1 is already in C here. So the next place to go now is B. Right, so 1 goes back to B. 1 goes back to B. Right, so that means we have 3 moves. 3 moves. So now we can't move 2, but we can move 3 now. 3 is already in A, so 3 goes towards C, AC. So 3 goes to C. So what we have here is 4 moves, right? So we are not left with 1 and 2, right? Because 3 has already gone to its destination pole, which is this, and it can't be moved anymore. So we are running on this between A and B in order for 1 and 2 to get to their own target pole, right? Between A and B, which is the source and auxiliary. So now what do we do here? So now the next thing to do is to move 1. 1 is already in B, right? Which is B. So coming here, man move back to A, right? Look at it. A, C, B, then A. A, C, B, then A. So 1 move back to A, right? So we now have 5 move, right? So we have moved 1. So the next thing to do is to move 2. So 2 is in B. So right. So 2 is supposed to move to A, but A is already has smaller number. So the next place to move to is C. So 2 moves down to C, right? Which we now have 6 move, right? So the last move is 1. 1 AC. So 1 is already in A, so it moves straight up to C. Now we now have 1, 2, 3 in our target pool, which completes what? Our 7 move. So it's a must that must be there. So anything less than this or greater than this, then it's wrong. So if you're doing n equal to 4, you should try n equal to 4. Now n equal to 4 should be 16. That is 2 times 2 times 2 times 2, 16 minus 1, which give you what? 15 moves. So try it and see. So n equal to 4 must give you 16 moves, and n equal to 4 follow this pattern. So try it and see and you get it. Right? It's very easy. So when you say n equal to 5, n equal to 5, right? So n equal to 5 will follow this pattern because 5 is an odd number. So it follows this pattern. Try it and you will get it, right? It's very simple. So now let's move on to our algorithm or recursive algorithm because algorithm work faster and very simple, right? So now computer actually doesn't actually makes that even and odd moves, right? But recursively, it decides on where the pole to on which pole to place the disks on, right? But it's the same if you check if you're writing this on the code, or this is not the coding class, but if you're writing this code, it follows this pattern, right? For odd number, you will see the move, which is ABC. For even number, sorry, ABC move. Then for odd number is ACB move, right? That is how it does recursively. That's how it does it recursively. So now the algorithm here, we have the function. Let's say we have a function called Hanoi, right? So we have our parameters. So our first parameter is n, which takes the number of disks. So the second parameter is our source. Then we have uh, our auxiliary, which is our temporary storage. Then we have our target, right? So now if n is equal to one disk, right? So just output. So just output uh n move n disks to n disks from source to target, right? So just move it one. So then if it's not equal to one disk, then perform a recursion, which is the 12 Hanoi recursion, 12 Hanoi. So to be then move all n disks, right? 12 and then move all n disks, which is n minus 1, excluding the last disks. They move all n disks, right? From the source pole, right? Then making the target pole as a temporary storage, right? Then moving it to the auxiliary pole, right? Then we are outputting move n disks from source to target. So doing this recursive algorithm, this is where everything being swapped when it's even or when it's odd. So it's swapped in, especially the target and the auxiliary do swapped when it detects that the n items even on the airtime and n items is odd. So it makes the move here, right? So at the end, the large number goes to at the end of everything here in the temporary storage after the all numbers have been placed, making way for the larger number. So at the end, the larger number move to the permanent to the target pool. So I have Hanoi. So the same n equal to 1, right? So the same n equal to 1. And then move all from this source, moving from every other thing from the auxiliary down to the target pool. Every other files from the auxiliary down to the target pool, right? So that is how the 12 Hanoi works, right? So at the end, I will output the 12 Hanoi. I'll put that 12 Hanoi. Then I can decide to put any disk I want to put here. Then my source, the auxiliary, which is a string, the source, the auxiliary, and then the target. So that is how the Torah panel works, right? Recursively, this is how it does this, and this is how it recursively make the move. So we have explained how the move works here theoretically and how you can solve that theoretically. Then if you're passing this instruction to computer, the computer decides that and then swap the target and auxiliary, especially when it detects the total number of ticks and then make its own decision. So recursively, that is how it works, and you can see the short line of code. So if you're writing in the Python, especially, you don't need to do much here. All you just need to do is to follow up the principle of how to write the algorithm here, and this will work perfectly fine. So I hope you understand this, right? But if you don't understand, this, please follow me on my YouTube channel where you can learn other programming language and other machine learning stuffs, right? And other artificial intelligence stuff and natural language processing technique in order to build intelligent systems. So thank you and God bless you.